Hi everyone, my name is Hayes Vinod, and today we'll be talking about primer vector theory. We'll start by discussing spacecraft trajectory optimization. We will then talk about the optimal control problem, and that'll lead us into primer vector theory itself. Some motivation for trajectory optimization. The reason we want to optimize a trajectory is it can help us decrease our fuel needed, and that'll help us decrease our mass needed. By decreasing our mass, we can make launch costs cheaper. We can increase the amount of scientific instruments we have, which will increase the scientific value of our mission, and we can also extend our mission lifetime. Much of the information from this textbook comes from much of this information for this lecture is from Bruce Conway's Spacecraft Trajectory Optimization, which is a really good textbook for studying spacecraft trajectory optimization. So here's some complications for trajectory optimization. The number one is that this dynamical system is not linear. We also have that practical trajectories can include discontinuities in your state variables. For examples, you can have an instantaneous delta V from using your rockets, or you can get that from a planetary flyby. You can also have instantaneous changes in your spacecraft's mass from staging, or the same delta V maneuvers. You can also have a sudden change because of coordinate transforms when you're switching from the gravitational sphere of influence from one body to another. You might not know the terminal conditions. You're either the initial or final or both of those conditions. For example, the for an interplanetary trajectory, your positions of the departure and arrival planets will depend on those terminal times, and that is a value you can optimize for. There can also be time-dependent forces or perturbations that we've discussed in class, and the structure of an optimal trajectory may not be based on theoretical deduction, but it's instead subject to optimization. For example, the number of impulses or the number of planetary flybys or what planets we use for these flybys are all subject to optimization. For the different types of optimization problems for spacecraft trajectories, we can break them into impulsive thrust problems and low continuous thrust problems. So our impulsive thrusts are sort of like our chemical propellant. Um, these are parameter optimization problems. And if you're only doing a single impulse, your unknowns are just your initial time, your initial delta V, and your final delta V. We can further complicate this by adding more impulses. Once you do that, you need to figure out the timing between these impulses, the magnitude of these impulses, and the direction of that impulse. This becomes really complicated when you add gravity assists. So now you have to figure out the number of flybys, the planets you want to fly by, the dates of the launch, the dates of the flyby altitude, any mid-course impulses needed. Uh, Compared to that, the low continuous thrust problem is a bit simpler. So this would be sort of your ion thrusters. These are continuous optimization problems, and your discrete unknowns are your initial time and final time. What you have to do with this is you need to find your thrust pointing angles and throttle value continuously along your trajectory. And you can also complicate this by adding gravity assists. This hasn't been done in practice, I believe, but I found a very good dissertation that's cited, and if you look at the end of the slide deck, that discusses how gravity assists can be used with continuous thrust problems. For different types of solution methods, we have our numerical methods, which finds the approximate solutions using iterative computations as well as numerical integration. This avoids being analytical by avoiding the necessary conditions of the calculus of variations, which I'll get into later. The analytical methods, they find exact solutions using mathematical formulas. You do have to sometimes use numerical methods with your analytical methods. Some examples are your classic Hohmann transfer, primer vector theory, which we're covering today, and shape-based trajectories in Hamilton-Jacobi theory. A third type of method, which is somewhat new, are evolutionary or meta-heuristic methods. So these are inspired by biology, and how they work is they randomly generate a bunch of different initial conditions. So it maintains a population of these initial conditions and selects the best individuals that are closest to local minimums. And some examples are genetic algorithms, as well as particle swarm optimizer, which is what my thesis will focus on. So looking at the optimal control problem, we start with our system equation, x dot equals to f of x, u, and t, where you know your initial state. So x is your state vector and u is your control vector. So your state vector could simply be x, y, z, and then your velocity in your x direction, velocity in y direction, velocity in z direction, while your control vector could be the thrust from your engine in the x, y, and z direction. Your terminal condition specifies your final state of the equation. So this could be the final position as well as like the final velocity your spacecraft must have. The objective function is your total cost and the function we want to minimize. The first term in that objective function is your terminal cost function, which sort of is the penalty for not reaching the exact spot you specify as your final place. The second term, your integral of the Lagrangian, is your cost accumulated during the trajectory. To derive the necessary conditions to find the minimum total cost for your system, you want to define a system Hamiltonian. Our system Hamiltonian is H equals to L, or your Lagrangian or your running cost, plus lambda t times F. So lambda t is your time-dependent vector of Lagrange multipliers. This vector is sometimes called your costate vector or your adjoint vector. If you need a refresher, Lagrange multipliers are the rate at which an optimized value, in this case cost, changes with respect to a small change in the constraint, which is x dot and our boundary conditions. Our necessary conditions include our costate dynamics. Lambda dot equals to the negative partial derivative of your Hamiltonian with respect to your state, with that given boundary condition that I'll discuss a bit later, as well as our optimal control law, which is our partial of our Hamiltonian with respect to our control vector should be 0. And if you don't have final time and you want to optimize your final time, you can use the following scalar equation to help optimize that. We can further define our optimal control problem by letting the derivative of our state vector be equal to the compound vector in which r dot, our time derivative of our position vector, is the first three terms, and v dot, the time derivative of our velocity vector, is the second three terms. Our time derivative of our dot, our time derivative of our position vector is simply our velocity vector, and the time derivative of our velocity vector is simply our acceleration vector. And in that case, g of r, our acceleration vector, is equal to g of r, which is our gravitational acceleration, and plus our thrust, which is symbolized using gamma, capital gamma, as our thrust acceleration magnitude, and u hat as a unit vector that indicates our thrust direction. To minimize our velocity change, we want to set L, or our Lagrangian or running cost, equal to our thrust, so that when we integrate our running cost over the initial time to the final time, that integrand would be equal to our delta V. Let's take a look at our system Hamiltonian. H equals to L plus our Lagrange multipliers times F. And we know that F is equal to R dot and V dot. And we can split up this vector and take the R terms, the first three terms that correspond to those position vectors, and call that lambda R, and we'll call that our adjoint vector for our position terms. And the adjoint terms with respect for the velocity terms would just be called our adjoint vectors for the velocity. And we can plug all those values in that we defined on the top of the slide deck and do some algebra to rearrange it into the final equation, which is our thrust times 1 plus our adjoint vector for the velocity terms times our u hat, plus the adjoint vector for your position terms times velocity, plus the adjoint vector of our velocity terms times our gravitational acceleration. Since we have this new form for our Hamiltonian, we can look at one of our necessary conditions, the optimal control constraint, and that's the partial of our Hamiltonian with respect to the partial of our control vector should be equal to 0. If we actually take the partial derivative of our Hamiltonian with respect to u, we get that the partial derivative is equal to thrust times the adjoint of our velocity. So this would imply that h is linear in u, and the only time this is equal to 0 is if our adjoint vector is 0 or our thrust is actually 0. So we can look at Pointryagrin's minimum principle, and he essentially says that the optimal control variables are instead picked to minimize our Hamiltonian. One way to minimize this Hamiltonian is to look at our first term in the Hamiltonian, the thrust times the 1 plus the adjoint of our velocity times the unit vector for our control. If we try and set it equal to 0, that would minimize our Hamiltonian. So we can get that the adjoint of the velocity times our u hat is equal to -1. And these two vectors are essentially a dot product with each other. So it would be equal to the magnitude of the adjoint times the magnitude of our u hat times cosine theta. And the magnitude of a unit vector is just 1. So we're left with the magnitude of the adjoint vector for our velocity times cosine theta is equal to -1. The case to make this -1 would be as if theta is equal to 0, which would mean our u hat and our adjoint vector for velocity should be parallel. So we can say that u hat is chosen to be parallel to the negative adjoint vector for a velocity, and now this negative adjoint vector for our velocity is called the primer vector. So the rest of the slide deck will follow Bruce Conway's Spacecraft Trajectory Optimization Chapter 2 by Prusing. We now have our new Hamiltonian in the form of adjoint vectors. So we want to find what our adjoint equation is using our costate dynamics equation. So if we take the partial of the Hamiltonian with respect to our position and our velocity, we can get these new equations, which basically say that the time derivative of our position adjoint vector is just our negative velocity adjoint vector times our gravitational gradient, or more specifically, the Jacobian of our gravity gradient, and that'll be a 3 by 3 matrix. The time derivative of our velocity adjoint vector is simply just a negative adjoint vector for your position. We can follow the same strategy with our terminal cost boundary conditions to get our terminal or our boundary conditions for our adjoint vectors. Psi can be rewritten in terms of our radius and velocity. And if we want to minimize psi, we can define phi to be our new and nu is another set of Lagrange multipliers that will minimize psi. When we take the partial of phi with respect to radius and the partial of phi with respect to velocity, we get these simple equations for our time derivative of our adjoint vectors for the radius and the adjoint vectors of velocity. From earlier, we defined the negative adjoint velocity vector as our primer vector. So for the future slides, we'll be using p of t equals to negative the adjoint vector of velocity. Our optimal thrust unit vector is pointing in the direction of the primer vector. So we can say u hat is equal to the primer vector itself divided by the magnitude of the primer vector. And we can use some vector algebra to yield that the adjoint of the velocity vector times u hat is equal to the magnitude of the negative magnitude of the primer vector. Using the relationships we made in the previous slide, as well as our definition for the primer vector, we can note that the time derivative of our primer vector is simply the adjoint vector for your position terms, and the second time derivative of your primer vector is equal to your gravitational gradient matrix times your primer vector. So the final equation on the previous slide is our primer vector differential equation that we can solve for to find our time history of the primer vector. The relationships in slide 11 that relate our adjoint vector to our terminal boundary conditions, as well as the relationships in slide 12 that define our primer vector with respect to the adjoint vectors, can give us new boundary conditions for um, our primer vector and its time derivative. And now that we've defined all that, we can now redefine our system Hamiltonian with respect to primer vectors and its magnitude instead of those adjoint vectors. So we now get our Hamiltonian is equal to negative of our primer vector magnitude minus 1 times the thrust, and that first term is sometimes called the switching function, plus the time derivative of our primer vector times our velocity vector plus the primer vector times our gravitational acceleration. So let's take a step back and try to get a physical interpretation for our Hamiltonian. Our first term, negative of our primer vector magnitude minus 1 times our thrust value, is our thrust term. And it basically tells us how beneficial thrusting is at a specific instant. So when p is greater than 1, you want your thrust to be as high as possible because your thrust is very effective. When your p is less than 1, you want your thrust to be 0. So your thruster should be turned off, your spacecraft is coasting. When p is equal to 1, your Hamiltonian is insensitive to thrust. And this is going to be the boundary between when your thruster should be off and is not helpful, and when your thruster is very effective. In practice, when your p is equal to 1, you'll immediately turn off your thruster, and then your primer vector magnitude should decrease. So your p would not get greater than 1. The second term of this Hamiltonian is the time derivative of your primer vector times velocity. And this quantifies how your spacecraft's motion is contributing to minimizing the Hamiltonian. And our final term is the primer vector times the gravitational acceleration. And that quantifies how gravity at your spacecraft's position contributes to minimizing the Hamiltonian. To actually solve our primer vector differential equation, we can rewrite it as the following, where you have the time derivative of you have your vector of your time derivative of your primer vector and the second time derivative of your primer vector. And that's equal to a matrix that has on the top left term, a 3 by 3 matrix of zeros, followed by a 3 by 3 matrix of um, of an identity matrix. The bottom left entry is your Jacobian of the gravity gradient, and that's followed by the another 3 by 3 matrix of zeros. And you multiply that by your primer vector and your time derivative of your primer vector. This is similar in form to y dot equals to a times y, which is a very popular differential equation. And our y of t would be equal to a state matrix times our state transition matrix times our initial conditions for y. So we can define a state transition matrix where we put filler matrices in there, which we're using as M, N, S, T, and we can solve this out and we'll know our P final and P dot final. And those equations are listed there. And a clarification on subscripts, your P sub F is just your primary vector at the final time. And when there's two subscripts, that refers to the final time as your first input and the initial time as your second input for the matrices. I believe the first time primary vector theory was derived, they applied it to optimal impulsive thrust. So just some more information on that. When we have a high thrust engine, we want to approximate our thrust as a Dirac delta function. This means that the thrust is happening over a zero duration and has an unbound magnitude. An example of this would just be your Hohmann transfer. When we're using optimal impulsive thrust, we have a set of impulsive necessary conditions we must meet. So first of which, we want to make sure that the primary vector and its first derivative are continuous everywhere. The magnitude of your primary vector is always less than or equal to 1, at which the impulses occur at those instances at which p equals 1, for reasons I mentioned earlier. At the impulse time, the primary vector is a unit vector in the optimal thrust direction. And this sort of ties in with 2, because your unit vector has a magnitude of 1. So we want to make sure that our p equals 1 at those impulse times. And then as a consequence of all those above conditions, your derivative of your primary vector, or p dot, is equal to p dot transposed times p equals 0 at an intermediate impulse that's not the initial and final time. To satisfy our third necessary condition, we want to make sure that the primary vector is our unit vector. So a unit vector along the direction of our delta v. So we just take our primary vector and we say that it's equal to the delta v at that time divided by the magnitude of delta v. And now with all the equations on slide 15, as well as having a known initial primary vector and primary vector rate, we can solve for our primary vector at any point, and it would be equal to that following equation. Here is an example of a Hohmann trajectory solved using primary vector theory from Prusing's chapter in Conway's spacecraft trajectory optimization. This case here uses canonical units. So OOP is original or initial orbit periods. The circle is the initial position and square is the final position. And pluses are impulses. So if you take a look at this trajectory, you see that it's going in its initial orbit, and as it goes on this initial orbit, you can see the primary vector going from close to 1 and slowly decreasing and increasing again. And this plus right here, or also right here, is when the primary vector reaches 1. So that is the location of the first impulse. And you can see it leaving the initial orbit and going in a orbital transfer. until it gets right here where we have another plus, and that is our second delta V to match that orbital velocity so that we can circularize our orbit. So this is a really cool analytical way to make sure your spacecraft trajectories are optimized. For my final project, I'm actually planning on trying to apply primary vector theory to satellite relative motion. Here's my citations. Again, most of the work on here is from Bruce Conway's spacecraft trajectory optimizations, specifically chapters 1 and 2. And please write down any comments you have on Canvas. Thank you.